Last time, we started to introduce to you the idea and concept of the Landau's free energy functional, which can describe finite temperature phase transitions. And today, we will formally define mathematically what that means, the Landau's free energy. So within this so-called phenomenological Landau theory, Landau proposed that we could write down a kind of a free energy functional, which is a function of temperature, the coupling constant, and the order parameter. So that's all it matters, right? So near the Tc, this called the Landau's free energy can be expanded as power series of order parameter phi, which means that if we defined a Landau's free energy density, which is the Landau's free energy divided by the volume, which I use the italic L to represent such a Landau's free energy density. This italic L can be expanded in power series of the order parameter phi, which means that we could expand the L, say constant A0 plus A1 times phi to the linear order in order parameter, and A2 phi square plus plus AN phi to the power of m. Because near Tc, the order parameter is really tiny. So from our previous experience studying the Ising model, we know that we are able to do such a expansion near the transition in powers series of this magnetization m. But in general, for many different all transitions, phase transitions occurring in finite temperature, Landau proposed that we can always write down such a kind of expansion as power series of the order parameter. So depending on these coefficients in front of this powers of order parameter, we can have a continuous transition or first order jump. Okay, so we will come back to this later. But in general, we can construct such a power series expansions of this order parameter near the transition, and that's what Landau suggested. The exact form of this power series expansion should be consistent with the symmetry of the system. For example, the rotational symmetry or time reversal symmetry and so on and so forth. And the state of the system is specified by the global minima of this Landau's free energy density. By global minima, I mean we should take the first derivative of Landau's free energy density, italic L, with respect to the order parameter phi, and we set it to be 0. Okay, so which means that in general, this Landau's free energy functional is a function of the order parameter phi, and in general, this phi could be a scalar vector and so on. So it lives in the multidimensional parameter space. So the stable state of the system should be given by the global minima of that Landau's free energy density. That's from the statistical analysis. The system that is stable is because it is a minima of free energy compared to other local minima or maximum points. And that's how we got the equation of state. Remember, the order parameter phi becomes finite at below Tc and 0 above Tc. So for example, the Ising model, this order parameter is given by the magnetization. So at zero field, h equals 0, and we'll see in just a moment that the number of terms in the expansion is actually even, which means that only the even terms with even powers of phi survives. All the odd powers in the expansion vanish. We could determine the equilibrium value of phi by taking the derivative of Landau's free energy density with respect to phi and set it to be 0, and in that case we get the 0 phi when t is above Tc and non-zero magnetization when t is below Tc. Okay, but this is more general than just the Ising model. We could discuss various kinds of transitions at Tc which could be analyzed in the same way. But there are some assumptions of the Landau's phenomenological theory of a phase transition. Number one, L should be consistent with the symmetry of the system. For example, is this ON or other types of symmetry? Then it should be respected here. Number 2, Landau's free energy density should be an analytic function in phi and the coupling constant k near the transition where phi vanishes. So remember, when we discussed this Ising model, we came up with the result that the free energy density is actually a function of the absolute square of the field. It is something different from the Landau's free energy functional. So in Landau's free energy density, it is the analytic function in both phi and coupling constant k. But even so, we could still get a phase transition based on this power series expansion. So we will see that in just a moment. And the third assumption is that in an inhomogeneous system, where we have a special inhomogeneous system with a spatially changing order parameter. And in such a case, this Landau's free energy density is a function of spatial coordinate and the gradient of phi as well. So remember, the Landau's free energy density is a function of the order parameter, but in a system where the order parameter is actually changing from position to position, namely the order parameters of, say, 2-dimensional or 3-dimensional or even 1-dimensional system are position dependent. In such an inhomogeneous system, in general, the Landau's free energy density is also a function of spatial degrees of freedom. Namely, the order parameter is a function of the position vector r and also the function of a gradient of this order parameter. Okay, so we will derive spatially inhomogeneous Landau's free energy density later. But this is a local function of phi, meaning we can locally define the Landau's free energy density at any given position, and we could take average or integral over such Landau's free energy density over the entire space. And number 4, as I just mentioned, this expression value of phi is actually given by the global minima of L of phi. Okay, so there's a remark. This kind of a power series expansion in principle is infinite terms. It has infinite number of terms in general. However, we do not keep all the way to infinite order in order parameter to have a phase transition. So the minimum number of terms that we can have a phase transition is to expand this L up to quartic term, phi to the 4th power, and that should be sufficient. Okay, but the validity of the truncation of the power series, the truncation of the power series for L depends on the dimension and codimension of the singular point. In some cases, we may need to expand the Landau's free energy density functional to higher order, but in other cases, just keep up to phi to the 4th power. That should be enough. Okay, but up to where we can truncate the power series expansion depends on the dimension and codimension of the system near the singular points. Okay, so let's just start to expand this L up to just a quartic term. We have A0 plus A1 phi, A2 phi squared, and A3 phi cubic, and A4 phi 4. Okay, so please note that these coefficients are purely phenomenological. Meaning there's no way that we could compute these coefficients exactly analytically or numerically. Okay, it's just cannot obtain this coefficient microscopically, or at least very difficult to obtain such coefficients in a microscopic model. And that's why we call this phenomenological theory. We assume that those coefficients A0, A1 up to AN are real numbers, and this phi is the order parameter, which can be a scalar or a vector. In the simplest example of the Ising model, this phi is just a scalar which is kind of a variable, unknown variable, to be determined by minimizing the Landau's free energy density with respect to phi. And those coefficients are the unknown coefficients in front of those powers of phi, and we can simply just know whether they are positive or negative. How to compute this A coefficients is a very difficult task microscopically. So we don't know how to exactly determine those coefficients, but we know they are either positive or negative real numbers to get a phase transition. So then this is the minima terms that we can keep to have a phase transition. Okay, so let's take a short break. To actually determine the coefficients in the power series expansions of Landau's free energy functional, as I mentioned, we could simply truncate this expansion up to just the fourth order in or quartic term in this mean field order parameter phi, and we should determine the value of the order parameter by minimizing the Landau's free energy functional with respect to the phi. And if I do so, I get this equation here, which should be 0, but we have many constraints need to be satisfied in order to determine whether those coefficients are finite or 0 or positive or negative. And the first criterion is that we need to have this result that this phi is 0 when temperature is above Tc and in the limit of 0 field. We need to satisfy this, and we immediately get that the A1 should be 0. Okay, because when temperature is above Tc, by the way, these coefficients and expansions are valid both above or below transition temperature. Okay, so this is always true above or below the transition temperature. So in other words, all these coefficients are functions of T or T minus Tc, because the only thing we can tune is to tune those coefficients as a function of temperature below above Tc, so that in one case we have an ordered phase, on the other case we don't have the finite order parameter. And so in general, those coefficients are functions of temperature, and especially they are functions of T minus Tc when T is very close to Tc. So if we want to satisfy this condition that above Tc there's no finite order parameter, then A1 should vanish. Okay, if A1 is finite, then we cannot have a situation where phi is 0 above Tc. So this is the first thing that we need to satisfy. So we have this first criterion satisfied by setting A1 to be 0. And second thing is the symmetry of the system. Remember that. Okay? So in the absence of the field, in the limit of 0 field, for example, in the Ising ferromagnet, we have discussed already that there's a symmetry between the probability of finding the Ising ferromagnet to be in the upspin state or downspin state. So they are the same. Remember that. If we don't apply the field, then there's an equal probability that we can find the spin state to be either pointing up or pointing down for Ising ferromagnet. And as a result, we can imagine that its probability is some kind of Boltzmann weight, which is given by this kind of an exponential e to the minus beta times some kind of free energy. And Landau's free energy functional serves precisely as some kind of a free energy. But it is different from the Gibbs free energy. We will discuss that later, but it can be regarded as some kind of a free energy. As a result, this L, this italic L, which is in the exponent of this probability distributions of finding either plus or minus phi. So as a result, this Landau's free energy density as a function of phi has that symmetry. So it is the same for plus phi and minus phi. Okay? So in other words, when we have such a symmetry of the Landau's free energy as function of phi and of minus phi, then if we expand this in terms of the power series in phi, and only the even power terms survive. So that's really obvious and that we can understand, because all the odd terms will not satisfy this symmetry. So we get rid of half of the coefficients already. So A1 is 0, A3 is 0, A5 0, all the way to A2n plus 1. And we only need to focus on the even power terms in this Landau's expansion. Okay, so that's what I write here, that in the zero field limit, Landau's free energy density is expanded in terms of only the even powers of phi and not odd power of phi. But of course, in the presence of the finite field, we are allowed to have the odd power terms in the Landau's expansion. So that's another story. We will discuss that later. But in the absence of fields, it can be expanded only in terms of even power terms. Okay, so say we get rid of this cubic terms and linear terms, and we can also get rid of the constant shift A0 term, because this Landau's free energy is some kind of a free energy. So A0 is a shift, a constant shift of that free energy, and which doesn't play any role when we discuss all this, say, order parameters and so on. Okay, so all this kind of calculation involve only the derivative of this free energy density with respect to the phi, and this A0 doesn't play any role. So we simply can just fix this A0 to be 0 and just forget about this A0 term. So then we have only two terms left, A2 and A4. But we also remember that we want not only the phi to be 0 above Tc, but we also need a non-zero finite phi to be observed when temperature is below Tc. But you can solve this some kind of a minimum condition for free energy density and find this expectation value of the phi is given by square root of minus A2 divided by 2 times A4. Right? You simply just solve this equation and get rid of this, and you know how to solve that. Or 0. So there are two possible roots of that equation, and one is 0, which is a trivial solution, which means that there is no order in the system. And in the case of the finite root, we get this given by a square root of minus A2 divided by 2 times A4. And this should not be 0 when we have ordered case. But we know that whenever t is less than Tc, and this phi is finite, but this is actually real, a real number. In other words, there should not be any negative thing inside the square root. In other words, to satisfy this, the real value of the order parameter below Tc, and also the value of the order parameter above Tc. So the only solution is that A2 is a function of temperature, and it is positive when T is actually above Tc, and it is negative when T is below Tc. And also, we assume that A4 is actually the positive number. So in other words, when A2 is positive and A4 is positive, then we get the square root of minus times something, which is purely imaginary, unphysical, and therefore this cannot be the solution. And therefore, for T above Tc, only 0 is the solution for phi. But when T is less than Tc and A2 is negative, but A4 is positive, then minus minus is actually plus, and square root of the plus positive number is actually a real number. So we do get a real valued order parameter below Tc. So from these two conditions, we concluded that A2 should change signs at Tc. So from positive above Tc to negative below Tc. And therefore, the simplest possible way to satisfy this temperature dependent of A2 coefficient is that it's proportional to T minus Tc, because it is positive when T is above Tc and negative it is below Tc. Or in simple terms, it is proportional to the little t dimensionless temperature, which is T minus Tc divided by Tc, which we introduced that already. So of course there's a prefactor, but we don't care too much about this prefactor, but we only care about this temperature dependence of the A2 coefficient. Okay, so we could determine the sign and the value of the A4 in a similar way that we could Taylor expand this A4 because we know that all these coefficients should also be function of t minus tc. And as t is very close to c, we could do power series expansions of A4 coefficients in terms of the constant term A40 plus the linear term in t minus tc and plus quadratic term and so on. But as t is very close to c, we could forget about the other higher order terms, only keep this constant terms and linear term. And we can also get rid of this linear term, and we could just approximate this A4 coefficient as just a constant, positive number, which leads to this non-zero real values mean field parameter below Tc. So that is sufficient for our purpose. So about this, the sign of this A4, as I mentioned, it should be positive, but from the square root solution of this phi, it can also be negative because then we change signs of A2. But from other considerations, A4 should be positive. Why? Because if A4 is negative, then we know that this Landau's free energy density is actually unbounded below. Because when A4 is actually negative, then in the case where this order parameter approaches infinity, then this Landau's free energy actually diverges, which becomes unphysical because any free energy of any theory should be finite in any case. And therefore, A4 should be negative. So we will make a plot of this Landau's free energy density as function of phi in just a moment to see this. If A4 is negative, then L in the limit of the phi goes to infinity becomes minus infinity, which is unbounded below, which means that the system is actually experiencing a kind of a catastrophe. Okay, so the particles will fall into that minus infinity energy levels without any bound. So which means that you have some kind of a minus infinity energy level which attracts all the particles to fall in, that kind of black hole stuff. But we know that there shouldn't exist such a negative energy state, negative infinity energy states in any physical system. So in other words, we should avoid such a kind of a no bound below situation, and A4 should be negative. So the final thing is that we can just discuss general situations for Ising model. This L, Landau free energy density, is given by this. So here we expand this power series up to phi to the power of 6. In some cases, we do need the power of 6. But we also include the field because we know that we can also apply the finite magnetic field to the Ising model. So that will be our starting point next time to analyze this, Landau's free energy functional in terms of a power series in phi. So before the end of our lecture today, I will make some remark. So this phi that we consider just over there is a scalar field. So we can also consider a more general case where we have a vector nature of an order parameter, such as in the Heisenberg system. This L, we know that the magnetization in the Heisenberg model is a vector in a three-dimensional spin space. And as a result, this Landau's free energy functional can be written in terms of power series in those vector expansions. And also the magnetic field could be pointed to any direction in the three-dimensional space. So the Zeeman term is actually the dot product between this H, the field direction, and the direction of the magnetization vector. And the square term, the quadratic term, is actually the magnitude of this vector. And the quadratic term is again the magnitude, the square magnitude, the square of the square magnitude of the phi vector. So I guess that should be enough for today. And next lecture, we will plot some figures of this Landau free energy density as function of phi and see how this continuous phase transitions occurred and how the first order transition can be possible in this phenomenological Landau's free energy formalism. Okay, so I'll see you on next Monday.